Hello everyone, very good morning. This is Rahul Kumar, and today we have our first session of Hadoop Administration Training. So here is the agenda for our Hadoop Administration class today. First of all, we're going to start with what is big data all about, and we're going to understand what is Hadoop itself, which is solutions to the big data problem. Then we'll just go through into some basics of what is Hadoop ecosystem and what are the different components involved in the Hadoop ecosystem, what are the different tools and technologies as well. Then we'll go into the basics of Hadoop core components like Hadoop distributed file system and yet another resource negotiator or yarn. And then we'll go into the Hadoop core configuration files. So the idea is to build a multiple node Hadoop cluster where we can configure all the Hadoop configuration files. And then we'll try to understand how different components work together, like your name node, data node, secondary name node from the HDFS side, and resource manager, node manager, and job history server on the yarn side and MapReduce side. At the end of the session, we'll try to understand the commissioning, decommissioning process, where we'll try to add one new node into the cluster and see how we can scale out the cluster, scale out the storage of the HDFS without bringing any nodes down or without having any downtime basically of the cluster itself. And then we'll also try to understand how we can decommission a data node, where basically we want to decrease the storage of the cluster by taking one data node out of the cluster itself. And then I'll also show you what are the different web user interfaces from daemons, like your name node, web user interface, resource manager, job history server, etc. And in the end, like as a conclusion, we'll try to understand what are the different job responsibilities of a Hadoop administrator, which administrator has to perform on a daily basis. And then we'll have a recap of everything. So this is how the agenda is, guys, for our today's session. And let's start with what is big data all about. Okay. So big data is basically a term for the collection of data sets so large and complex that it becomes difficult to process using on-hand database management tools or traditional data processing applications. So big data, guys, is basically a term which is utilized to define the big data or huge data, and the data which is so large and complex that it becomes difficult to analyze that data using our traditional database management tools. So you can do that, I mean, obviously, but then it becomes very difficult because the data sets are so large, complex, and rapidly changing that they push the very limits of our analytical capability. Okay. It also refers to a combination of an approach to informing decision making with analytical insights derived from the data, and also a set of enabling technologies that enable that insight to be economically derived from at times very large or diverse sources of the data. A lot of people have given the definitions of big data. It also refers to the approach to the data of collect it now and sort it out later on. So meaning you capture the data and store that data on a very large volumes of actions and transactions of different types on a continuous basis in order to make the sense out of it later on. Big data is a term just to define huge data in terabytes and petabytes we're talking about. So this data, why it is increasing so much now? Because of the IoT, the network of devices, vehicles, buildings, and other items embedded with electronics, softwares, sensors, and network connectivity that enable these objects to collect and exchange the data. So this data is getting increased because of the digital universe, which is going from 4 zettabytes of data in 2013 to 44 zettabytes of data in 2020. That's a prediction that how the data is going to grow actually. What makes this database big? So there are a couple of characteristics, or there are a couple of V's which are associated with this big data. For example, you can see here volume, variety, velocity, value, and veracity. So the idea is that these all are the characteristics of this big data. So first of all, which is volume. Volume is increasing huge data sets. So volume basically refers to the amount of the data sets being generated. Okay. Now you can think in terms of gigabytes, terabytes, and petabytes. And many systems and applications, they are just not able to store the data. Forget about ingesting or processing that much of data itself. Then you have got something called as variety. Variety refers to the number of types of data being generated. Okay, data can be gathered from the databases like your XML or JSON files, text documents, emails, videos, audios, stock data, financial transactions. All that basically comprises of your variety of the data. Generally, it is in like 3 types: structured data, semi-structured data, as well as unstructured data of the data. Then you have got the velocity. Velocity is the term which refers to the rate at which this new data is getting generated. Okay. Now think again in terms of megabytes per second or gigabytes per second. Okay. So data today is streaming. As you can see, it's streaming at an unprecedented speeds, and it must be dealt within a timely manner in order to extract the maximum value from the data. Okay. So there are different sources of the data. For example, you have got social media data, logs data, RFID tags data, sensors data, smart metering data. All these includes your velocity of the data. Then you got the value of the data. So value basically means that how all these data available, okay, how it will create a lot of value for the organizations or societies and the consumers. Okay. Now, big data means big business and every industry will reap the benefits from the big data. So, of course, just the data itself is not valuable at all. The value is in the analysis done on that data and how the data is turned into information and eventually how it is turning it into the knowledge. So, the value is in how organizations will use that data and turn their organization into an information-centric company that relies on the insights derived from the data analysis for their decision making. And then in the last, you have got something called as veracity. Veracity refers to the biases of the noise and the abnormality in the data. Okay, it refers to basically the trustworthiness of the data. So, can a manager rely on the fact that the data is representative? Now, everyone knows that there are inherent discrepancies in all the data collected. Okay, so when you have collected a lot of data in different volumes and when it is coming in at a different speeds, it's worthless if the data is incorrect. Okay, incorrect data can always cause a lot of problems for the organizations as well as for the consumers. So organizations, they need to ensure that the data is correct as well as the analysis performed on the data that is also correct, especially in your automated decision making where no human is involved anymore. Okay, so you need to always be sure that both the data and the analysis, they are correct. So these are the 5 ways they constitute your big data, and every big data has at least these 3 characteristics of volume, velocity, variety, and then some more ways have been included by other industry analysts to define the big data itself. So Hadoop is the solutions to the big data. When we talk about the solution, Hadoop is a framework that allows us to store and process large data sets in parallel and distributed fashion. So basically, when we talk about Hadoop, okay, it's a framework that allows the storage of any type of data, most of which would have been discarded in the past because making it usable would have been too difficult and expensive. And the value of this big data and Hadoop comes through on-the-fly modeling of the data that might actually be useful and which, when integrated with existing big data and analytical environment, can enrich your business insights. So what is Hadoop itself? Hadoop is a collection of open source software frameworks for the distributed storing and processing of the large sets of data. Okay, so its development is a community effort governed under the licensing of the Apache Software Foundation, and anyone really can help to improve Hadoop by adding the features, fixing software bugs, or improving the performance and the scalability. Okay, so it has got 2 important components. One is called Hadoop Distributed File System, which is the storage layer of it, where you can dump any kind of data across the cluster. What is a clusters? Clusters are basically created using the commodity enterprise grade hardware, which not only reduces the original purchase price, but potentially also reduces the support cost as well. And second component is called MapReduce processing. So MapReduce processing basically allows the parallel processing of the data stored in the Hadoop distributed file system. So today, in the version 2, we have got Yarn as well. So Yarn is more of a generic framework which can run MapReduce jobs, which can run test jobs or Spark jobs. All these kind of jobs can be run using the yet another resource negotiator or Yarn. So we got this kind of a architecture for Hadoop where we have one master node and slaves are connected to the master. And once I will proceed, I'll talk about a lot of other sub-components of Hadoop distributed file system and MapReduce or Yarn. So what are the different types of data? Let's talk about that as well quickly. We have different types of data today in the market. For example, we have got sentiments data, where you try to understand how your customers feel about your brand and the products right now. You have geographical data, which analyzes location-based data to manage the operations where they occur. Server logs, text data, clickstream data. Clickstream data is basically to capture and analyze the website's visitor data trails and optimize your websites. These are the different types of data available today. And then to extend the capabilities of Hadoop, because Hadoop is more of a raw storage and the processing power. However, this storage is distributed and the processing is also distributed. But then to extend the capabilities of Hadoop, we have some more Hadoop ecosystem components. Okay, for example, we have got Hive and Drill, which provides the analytical capability via SQL. So rather than writing a long MapReduce jobs in Java or Python or Ruby kind of languages, you use SQL, structured query languages. So anyone coming from the database backgrounds, they can easily start writing the Hive queries on top of Hadoop, and they can start quickly analyzing the data. Then you got something called as Uzi, which is used for the scheduling part. So when you create your jobs and when you create your queries, if you want to schedule them on a time basis or the databases, you can use something called as this Uzi as a workflow scheduler. You can create a workflow of multiple jobs in the Uzi, and you can run them on a particular time, at a particular time if you want. Then you got the Spark in-memory data flow engine, Kafka and Storm. So they are more of a data analytics software only, where you can analyze your data in memory rather than doing it on the disk via MapReduce. You do the in-memory processing via Spark. And Kafka and Storm are more of a streaming engines only, where you will bring the data, where the streaming data is coming, and you bring them via Kafka and Storm into the Hadoop distributed file system. Then there are some other components like HBase, which is a NoSQL database for your cluster. So you put the data via HBase, and the data is going to get stored inside the Hadoop distributed file system. It's a NoSQL database. Basically, there is no SQL support inside in this HBase, but then you can store all the streaming data and all the unstructured data in the HBase, and you can analyze it from here. Similarly, you have got Solar for searching and indexing purposes. You have Pig for analyzing the data via Pig scripts. You have got Mahout and Spark machine learning libraries, which you can put in the big data cluster. So when we say big data cluster comprises of all these components. Okay, all these other tools and technologies through which you bring the data into the Hadoop distributed file system, and you have Yarn as a resource management on top of it. And all these tools, they work together to create one application. Okay, if you want to import, export any data, let's say, so there are two tools like Flume and Scoop. So Flume is used to import the unstructured and semi-structured data, like you want to bring the Twitter's data, Facebook data, LinkedIn data, or any streaming data into the Hadoop distributed file system. You can use a tool called Flume for that. And then if you want to import and export any RDBMS data, okay, or any data warehouses data, for example, Netezza, Oracle, PostgreSQL, Teradata, all that kind of data can be bring in into the HDFS via Scoop. Okay. So this is the entire big data Hadoop ecosystem. And then on top of it, you can have tool like Apache Ambari or Cloudera Manager, through which you will manage the entire big data Hadoop cluster, and through which these all components will coordinate together so that they can work with each other. So this is the entire Hadoop ecosystem, guys, which generally the expectation for a Hadoop administrator is to have the basic idea of all these technologies to start with, and then go a bit deep, so that in case of any issues where developers are facing, they can help them to resolve these issues by having some idea of these technologies itself. So let's move ahead and talk about the Hadoop core components, where we have got two parts. One is the storage, as I said, and then you have got processing. So storage consists of the Hadoop distributed file system, where it has got three sub-components. One is the name node, then it has the data nodes, and then it has got the secondary name node. And similar to it, in the processing part, we have got Yarn, which consists of your MapReduce as well as other processing frameworks. And it has got its subcomponents like Resource Manager and Node Manager. And it has got some more subcomponents which gets generated during the job run, which are basically your application master and Yarn child containers. So how these components work, or what are their functionalities of these components? Let's go into that. So let's start with the Hadoop distributed file system first. So Hadoop distributed file system basically has got three components. One is the name node, then you have got data node and secondary name node. Now name node is the master of the system, guys. Basically it's the heart of the Hadoop distributed file system, or heart of the Hadoop cluster, I would say, because it contains the metadata of the data. Okay, metadata means all the locations of the blocks which are being stored, or the size of the files, permissions, hierarchy, timestamp of the file, replication factor, block size, everything gets stored inside the name node's metadata. Okay, so when you store a file into the Hadoop distributed file system, the file gets converted into the form of blocks. Okay, so here is a small example. Let's say I have this file of 1 gigabyte. What happens is, when you store this file into the HDFS, okay, this HDFS consists of multiple nodes. Okay, so when you store this file into the HDFS, this file gets converted into the form of blocks. Okay, And the size of this block is defined as generally 128 megabytes by default, but then Hadoop admins or Hadoop developers can decide that, okay, what block size they want. Okay, so if I try to store 1 gigabyte file with a block size of 128 megabytes, then obviously it is going to create 8 blocks in the HDFS. How come 8 blocks? So 1 gigabyte is like 1024, and you divide it by 128, it comes out to be 8 blocks in the Hadoop distributed file system. So name node, it is storing the information about these blocks, okay, and the files. It doesn't store any data. The actual data goes inside the data node. Okay, so data node are the slave daemons which stores the actual blocks of the data. Okay, data node actually stores the blocks of the data, and they serve all the read and write requests from the clients. Let's say clients want to read the data or write the data. They are the ones who will serve all the read and write requests. Okay, initially it goes to the name node, but then name node provides the information, okay, that these blocks are stored in these data nodes, and then clients start serving all these read and write requests from there on. So then you have got secondary name node. Okay, secondary name node is the checkpointing node, where it is responsible for combining the edit logs and the FS image from the name node. It generally does the backup every hour after hour, but then the idea is that you should always have a copy of the name node's metadata, which is being stored by the secondary name node. Okay, so how it works in the cluster, you will always have name node, one name node per Hadoop cluster. There will always be one name node per Hadoop cluster, unless you are implementing the Hadoop federation. Then you will have multiple data nodes because the actual data goes inside the data nodes. And then you have got the secondary name node. So it's also one secondary name node for one name node where you can store the backup of the entire metadata. Secondary name node does the automatic backup anyways, but then you can configure that how frequently it should do the backup. So let's go into the HDFS architecture. So this is what I was saying about the HDFS architecture, where you will have one name node and multiple data nodes here. And this is the HDFS client who is trying to put the data inside the data nodes or inside the HDFS, or it will read and write the data basically. So when you store a file into the name node, these are the kind of blocks which gets generated. You can see here the blocks in red, green, and orange. And eventually these blocks goes into the disks associated with the nodes itself. So secondary name node is doing all the backup operations here and for the metadata, and actual data goes inside the data node. So generally you implement something called as replication factor as well. Replication factor defines the multiple copies of the data. So when you store the data or when you store a file inside the HDFS, how many times you want that file to be copied again, or you want the number of copies to be created, so that in case one of the copy got lost because let's say the data node goes down, then how will you make sure, then how will you get that other copy of the data? You will basically try to bring the data from the other copy of the data nodes. Okay. So there was a question from one of the participants which asked, does Hive support all the SQL statements? Well, it won't support all the SQL statements, but then yes, it supports most of the SQL statements in the Hadoop cluster. So like transactions are not being supported by Hive. Okay, updates are not being supported. So there we can say some statements are still not being supported, but then according to the Hadoop distributed file system, most of the support is available in Hive today. So let's proceed and let's talk about the Yarn core components. Now there are various Yarn components today, guys, for basically processing the data which is there in the Hadoop distributed file system. To start with, it has got resource manager, which is more of a master daemon for the Hadoop cluster for processing the data. So resource manager is responsible for the resource management, and it has the visibility of how many resources are available so that it can take the jobs and start running those jobs in the cluster. Okay. Generally, we put it on a separate node which is having high quality hardware, because without resource manager, the jobs will not be able to run. So there will always be one resource manager per Hadoop cluster. Then you have got something called as node manager. Node manager is always deployed on the data node. Now, the idea is that node manager creates the containers for running the applications, and it monitors the resources on the data node. So containers are nothing but the allocation of the group of resources in the form of memory and CPU on every slave node. So whenever you submit a job, basically the job generates whatever the mappers and reducers are being generated, they run in the containers only. So these containers are created by the node managers when requested by the application master. And then you have got the application master. So application master is one per application. So whenever you submit, let's say, an application into the yarn, it generates an application master which coordinates and manages the MapReduce jobs, and it also negotiates your resources with the resource manager to schedule the task. So in yarn, the idea is that resource management part and the job management part is segregated. Okay, so resource management is being taken care by the resource manager and the node manager, and job management is being taken care by the application master and the container. Once you submit a job, the resource manager and node manager, they're responsible that the resources which are being required, they should be allocated. And who it is going to allocate to? It is going to start a new application master. Application master will manage the life cycle of the job, and whatever the resources are required by the application master, that will be given by the resource manager by creating the containers. So resource manager will send the request to the node managers, and node managers will create the containers for the application master. So question here, that why do we run the node manager in the data node? So the idea is that map and reduce containers, okay, which are being generated by the node manager, those containers have to process the data. Okay, obviously the data lies inside the data node. Okay, or you can say the blocks of the data lies inside the data node. So to gain the benefit of the data locality, containers are being, or the node managers, they are being deployed on the data node, so that when the containers are being generated, the data can be processed as fast as possible, because the containers goes to the data, process the data and bring back the results, rather than data traveling to the containers, which can take a lot of time, process of the data. So here in this case, the containers process the data and bring back the results to the application master. So we'll also go into the, how does the job actually run in the cluster. But this is how the yarn architecture looks like. Here you can see that the client who submits a job to the resource manager, there are multiple node managers deployed on every data node. And then for 3 applications, you can see 3 application masters. And then for each and every application master, there are multiple containers created for it. Okay, that depends upon how many containers are being required for every application you have submitted. But then for every application, there will be multiple containers created, so that the mappers and reducers can be submitted into those, or they can be processed into those containers. So this is the overall picture of your Hadoop cluster, guys, where you can see that all these nodes are being placed in the racks, and you can see one of the rack has got some master processes like name node and secondary name node, and all these are your slave nodes. Okay, and all these are being connected via switches, and then you have a core switch through which all the racks are being connected. So the idea is that when you have a large number of nodes, okay, they, instead of placing them just into the data center, you put them into the racks, and it saves a lot of space, as well as it always increase the performance of a cluster, because nodes are always nodes are together in that scenario. So let's talk about how we can build the Hadoop cluster, okay, and which one is being created in the organization. So you have got 3 Hadoop cluster modes: standalone or the local mode, pseudo distributed mode, and the multi-node cluster mode. So basically, to start with the standalone or the local mode, in this scenario, there is no Hadoop daemons. Okay, so generally, your name node, secondary name node, data node, resource manager, and the node manager, they're all called as daemons, or the processes, because they run in the background, so you call them as a daemons. And everything in this mode runs in a single JVM. And the idea is that it is just suitable for running the MapReduce programs during development. There is no actual Hadoop distributed file system, and it does not have any HDFS storage. It just runs on the local storage, and all the daemons run in the single JVM. So this is suitable for running MapReduce programs during development, but then you don't really run into the production with this kind of mode, because it's just a single node Hadoop cluster. Then you have got pseudo distributed mode. This is more of a simulation of your actual Hadoop cluster, with all the Hadoop daemons, they run on the local machine or a single machine, where you will have name node, secondary name node, resource manager, data node, job history server, and node manager on the single node itself. So it's a simulation, because you will have Hadoop distributed file system, as well as you will also see yarn daemons coming into the picture. So it shows how the Hadoop cluster is being created on the single node itself, which is called pseudo distributed mode. And the actual environment is basically your multi-node cluster mode, or a fully distributed Hadoop cluster. The idea is that you are going to run Hadoop daemons on a cluster of machines. Okay, so when we say cluster of machines, you will have more than 2 or 3 nodes in the cluster, which can span to like hundreds or 200s or 1,000 nodes as well, or it can more than that. And the idea is that the daemons or the processes are being run on these group of machines or the cluster of machines. Okay, So earlier we have seen how the cluster is being created. So this is the fully distributed node Hadoop cluster where you will have the name node, secondary name node, they're being deployed on the separate machine. Similarly, you will have other Hadoop daemons deployed on the separate machines, and then you will have slave nodes where you will deploy your slave daemons like DataNode and the node manager. So how the cluster hardware specification is, what kind of hardware is specified for creating a Hadoop cluster? So the importance of the daemon depends upon what is the work of the daemon. For example, we have name node, which is very critical for the Hadoop cluster to run. Without name node, nothing will work and Hadoop cluster will be down. So you give it a reliable hardware for the name node. So you also configure the high availability for it, which is basically being shown in our next session. I'm going to show you how you can enable the high availability. But the idea is that you provide a lot of RAM to this node, not much hard disk, because you don't store that much of data on the name node. It just stores the metadata, which is not huge in size. Good processor, Xenon processor with octa core, and then you have got Ethernet cards, so multiple Ethernet cards. Operating system, 64-bit operating system, and then redundant power supplies so that you can provide the power in case anything goes wrong with the node. Actual data does not go into the name node, as I said earlier. Actual data goes into the data nodes. That is why we have a lot of hard disk here. You can see 6 disks of 2 terabyte each, and you will have multiple data nodes. So you don't need a lot of RAM on the data node because the data is going to be processed distributively, obviously on multiple data nodes, because all the node managers are also going to be deployed on the data node. So processor of Xenon with 2 cores, Ethernet cards, 3 Ethernet cards of 10 gigabits, and operating system of 64-bit. Now, the same kind of reliable hardware we provide to the secondary name node with almost the same configuration. It is recommended to configure high availability. And when you have HA, then obviously you don't need the secondary name node. So secondary name node cannot run when you have standby name node. So if you do not have, let's say, so what you do is you create a secondary name node. Okay, and the idea is you can rebuild the primary name node from here. So this is how the Hadoop cluster hardware specification is. We have more recommendations around it. Obviously, we'll talk about it later on. And then you have got Hadoop configuration files. Let's talk about the configurations because we are going to start building the Hadoop cluster in a while. So you have got 6 configuration files which you have to edit. And to start with, you have got core-site.xml, which is located in the /etc/Hadoop folder of Hadoop folder itself. Okay, so you have a root Hadoop folder, and inside the etc and you have Hadoop folder, and then you have got these configuration files like core-site.xml. Core-site.xml, guys, is responsible for all the IOs with the HDFS. Okay, so basically it contains the HDFS URI, which is in the form of HDFS://. So something like this, HDFS://, and the IP address of name node. And port number is generally 8020, the default port number, but then you can always change it, which you want. So core-site.xml contains the configuration settings for your Hadoop core, such as IO settings that are common to HDFS and MapReduce. So you can say the temporary directory here, you can put the React topology scripts here, you can put the other IO related settings inside the core-site.xml, like trash server as well. Then you have got the hdfs-site.xml. As the name suggests, it is used for the configuration settings for your HDFS daemons, like name nodes, metadata storage, secondary name node storage, data node storage, replication factor, block size, permissions. All these settings goes inside the Hadoop distributed file system or hdfs-site.xml file. Then you have got the mapred-site.xml. So mapred-site.xml is being created. We have to actually create a copy of it. The reason is you can run other frameworks. As I said, you can run Spark as well in the yarn. You can run Tez as well in the yarn. You can run Giraffe jobs. You can run OpenMPI jobs. So a lot of other frameworks are being supported as well in yarn. MapReduce obviously is one of them. Of course, it is one of them, the prime one. And it contains all the MapReduce specific configuration settings. Like you can also define one of the other daemons which I have not explained earlier, which is called as job history server, which is used to manage the history of the jobs. Okay, if you want to manage the history of the jobs, you can create a job history server, and all the configuration related to the MapReduce, like your sorting factor, spilling factor, compression settings, or the heap size of your mappers, reducers, all such settings goes inside the mapred-site.xml. And then you have got the yarn-site.xml, which contains the configuration settings for yarn daemons, like your resource manager, where the resource manager is going to run, where the node manager is going to run. All these settings goes inside the yarn-site.xml. A lot of settings can go inside the yarn. For example, you can define the resource manager, node manager configurations, and the node manager's memory configurations, maximum amount of memory a container can take, minimum amount of memory a container can take, minimum maximum for the virtual cores as well for the containers. You can define all those settings inside the yarn-site.xml. We're going to take a look of these configurations files. So give it a minute, guys. Then you've got Hadoop environment.sh settings, Hadoop env, which specifies your environment variables that affect the JDK used by the Hadoop daemon. So basically it is responsible for your configuring the Java development kit, which is used by the Hadoop daemon, and other settings like your heap sizes, or you can define the log directories, you can define the process ID directory. All those settings goes inside the Hadoop environment.sh. And lastly, the very important file is slaves file. Basically, it contains a list of machines specified against each data node and node manager. So whatever the number of data nodes and the node managers you want to deploy, you put those list of machines inside this slaves file. Okay. So let's say you have got 10 data nodes. So all these 10 host names or the IP addresses you will provide into this slaves file, so that those machines can connect with the name node and the resource manager depending upon the data nodes and the node manager slaves file. So these are the configuration files, guys, that we have to edit initially to start a Hadoop cluster. And here, let's start the multi-node Hadoop cluster installation. So I provided a demo on how these files are going to be edited. So to start with, first of all, here I have created a virtual machine of Hadoop. And in this, the idea is to understand how we can create a multi-node cluster of Hadoop. So we'll start quickly. I'll just create one node itself here. 1 second, and I'm going to put it on the putty session. So that's a putty session I have, and we can use, this is the IP address I have given. So this is the IP address I have given for this particular node. And what we are going to do is we are going to quickly configure the settings into this one node. And what we'll do is after that, we'll just create 6 copies of this, and then we'll try to complete the cluster build. What we have to do in this scenario is, first of all, we'll download the software. Okay. So software generally are required as JDK and Hadoop. Okay, we're going to use Hadoop 2.7.3, and then we'll create user and group, and then we will edit the configuration files. Okay, so we'll create the passwordless SSH also. For that, I will passwordless SSH. Passwordless SSH simply means that you are enabling the SSH access without asking any passwords. And for that, you need to generate the public private keys and put it into the authorized keys file. And then you will edit the configuration files. And after that, you will create 6 copies of the single machine so that configurations can be deployed there automatically. And then you will format the name node, basically initializing your Hadoop distributed file system. And then you will start the daemons. Okay, so this is the approach I'm going to take. First of all, let us enable the passwordless SSH in this root itself. So for that, you have generated the public private key pair by running the command ssh-keygen. What it has done, it has generated a public key .pub and private key as this one. And then you will run the command ssh copy ID. And then for this host, you will enable the passwordless SSH just for root. Okay, this is the passwordless SSH for root, guys, nothing much. So if I just do a SSH on this node, you can see without any passwords, it is able to do an SSH into this node itself. And now what we are going to do is we're going to download the softwares. I'm going to use the Hadoop 2.7.3, and for that I'll just open the Chrome, and here we'll say Hadoop 2.7.3. This is what we want to download. So this is the one of the latest distributions, and here this is the file we're going to download, guys. Hadoop 2.7.3 tar.gz file. I'll just copy this address and I'll say wget, and it will start downloading. So size of this file is, guys, around 204 megabytes, which can take some time, around 10 to 15, 20 seconds. Almost done, 60-70%. And here you can see the file has almost completed downloaded. So we have got this Hadoop 2.7.3, which is around 205 megabytes. And we also have, I already have one JDK as well inside this. So this is what we need. JDK is Java Development Kit, which is very important for this cluster to run. And we have this JDK also inside this virtual machine. So let's create a group first. Let's say the group name is Hadoop and the user is also Hadoop. And I'll add this user into the Hadoop group. and let's change the password of this Hadoop user in the Hadoop group. And I will now move these softwares Hadoop 2.7.3 into the home directory, and I'll also move this JDK into the home Hadoop directory. So right now we have these softwares into the home Hadoop directory. We'll change the ownership of both these softwares and switch user to our Hadoop user here. So you can see there are two softwares now. So I'll extract the Hadoop 2.7.3 by running the tar zxvf command. And here you can see it has created these folder Hadoop 2.7.3, and then I'll also extract the JDK, and it is going to create our second folder of JDK. That's the kind of folder it's going to create. So I'll just create a symlink of both these folders. Okay, so these are the two softwares we are going to use to build our Hadoop cluster. Let's quickly go inside the Hadoop folder to see what all components are there, or what all directories are there. So we got bin directory, we got sbin directory. Bin directory basically contains your all the clients, Hadoop client, HDFS client, mapred client, yarn client, to connect to the cluster and then accordingly to query the data or run the jobs in the cluster. You got sbin directory, which contains your Hadoop scripts to start and stop the Hadoop daemons. For example, to start and stop the DFS daemons, you run start dfs.sh and stop dfs.sh scripts. To start and stop the yarn daemons, you run start yarn.sh script and stop yarn.sh script. To start the job history server, you run the mr job history daemon. This will start your and stop your job history server in the cluster. So we'll run these scripts, and all the configuration files goes inside the etc Hadoop folder. So Hadoop etc Hadoop folder is the one, which is what I was showing you earlier about the configuration files. The configuration files goes inside the etc Hadoop folder here. And here there are a lot of other files apart from these core configuration files. So we have got this core site.xml, we got the hdfs-site.xml, we got yarn-site.xml, then we got slaves file. What else? We got Hadoop environment.sh file, and we also have the mapred-site.xml, but it is in the form of template, so we have to create a actual mapred-site.xml file. So once we have this, the next step is to understand these configurations here. So first of all, we have got Hadoop environment.sh file is where we're going to put the Java home. So where the Java home is going to be created, that is the one thing we need to create in this. We have to export the Java home location. Then we have to export the heap size, Hadoop heap size, how much of maximum amount of heap can be used or the memory can be used. And we can also define the PID directory where the daemons or process ID files are going to be stored. Okay, you can define really any directory to it, but we generally use home Hadoop for making it easy. So before I do that, I will edit the bash profile file so that I can export the home directories of this so that I don't need to use the actual full path for them. So I've created some of the configurations here and I'm going to use it. This is the path I'm going to use. And here you can see my home Hadoop home is this folder, home Hadoop, and JDK is home Hadoop JDK. And what I'm exporting here is in the path, I'm saying export the Hadoop home and Hadoop home bin as well as Hadoop home sbin directory, because here my all these scripts are located. And I have got Java home and Java home bin so that I can use a command called JPS, which is located inside the JDK directory. JPS is being used to show all the Java processes currently running Java processes in the cluster. And Java processes are more of a, all these name node, data nodes, they're all nothing but the Java processes only. So if I want to view all the Java processes, I can use JPS command for that. What I will do is I will also enable the passwordless SSH here. It will just make my life easy to copy the files or anything later on. So you can see now passwordless SSH has been enabled here as well. So once we have this, we will also do one more thing. We'll also edit our etc host file, and here we'll put all the 6 nodes which we are going to create. In fact, 7 nodes, including our edge node as well. Edge node is the node which is being used by the Hadoop developers for accessing the Hadoop cluster. Okay, all the nodes can be accessed by administrators, but developers cannot access any other node apart from the edge node. So we'll create 7 nodes for our Hadoop cluster. So save and exit and just switch user to Hadoop. Let's start with the configuration of the Hadoop environment.sh. And here we will, first of all, we'll go into the Java home, and my Java lies inside the /home/hadoop/jdk. We can define the Hadoop heap size. The default is 1000 megabytes, and let's say it is 2000 megabytes for me. And then we can define a lot of other configurations, as you can see, but I'm going to use the only configuration process ID directory. So that's the process ID directory I'm going to export here. But generally, in the standard configurations, obviously it will not go into the home Hadoop, it will go into the var run directories, right? So that will be there. And then we'll go into the core site.xml. So core site.xml, as I said earlier, it contains the configurations of your IO settings basically for your HDFS. And these are the configuration files it has. So you will have fs.defaultfs, which is basically your file system location. And it is on the Hadoop distributed file system. It is hdfs://. This is the IP address where I'm going to run the name node 192.168.0.51. And the port number is 8020. This is a default port, guys. However, you can always change it from 1024. Basically, all the non-privileged ports can be created here. And then you have got the temporary directory. Temporary directory is going to store all the temporary data. Right now, there's no temporary data because I'm going to place everything inside the HDFS site. So let's configure the hdfs-site.xml. And here, these are the configurations I'm going to do for our hdfs-site.xml. So what does this contain? This contains our replication factor. So we have 3 data nodes. And as I said, the replication factor defines the number of copies you want to have in your for the data. So we want to have, by default, the replication factor is 3 as well. Here we are just trying to show the property that this is how you will define the replication factor. If the data is too much critical, then obviously you want to have more copies of it. Depending upon the storage cost, you can really bear up. So the replication is 3, so it will generate 3 copies of this data. Then Hadoop will not check for the permission, so we have make it false. We have set false to it. And then we are defining the metadata directory for the name node, which is basically in your home Hadoop data name node. And this is for the DataNode data directories. I'll go through a bit about the replication factor here by the slide as well. This is the replication factor here. Let's say you want to put any file, it will show you that's the replication factor of your file you have put inside the HDFS. So we are moving the test.txt into the HDFS. This is how you will list the file. So let's say there is one file over there, and then this is showing the replication factor here. Right now we are disabling the permissions, and if it is true, then it will enable the permission checking on the HDFS. Yeah, so this is the one I was saying. So we have got this name node metadata directory where FS image will be stored. Okay, so basically your FS image and edit files are going to be stored in this directory. And I was saying that generally you create a separate disk. So basically 2 disks have been created and put them into the RAID to avoid any kind of failures of or anything goes with the disk itself. You can still get the data from the other disk. And then you have got the DataNode data directory. So this is a local directory where your actual blocks are going to be stored. So DFS data will be stored here in the form of blocks inside the DataNode data directory. That's what we have configured here. Then you have got the block size. You can configure the block size of your HDFS like this, dfs.block_size parameter. This is what we have configured as well. It is in the form of bytes here. So right now this is 128 megabytes. So example is being shown here that if you're trying to store a file, let's say file.xml. Okay. If you want to store this file, if you want to move this file into the HDFS, it will be stored with 128 megabyte block size. So depending upon the size itself, these blocks are going to be created inside the HDFS. So then you have got the secondary name node address. So secondary name node is being created via this property dfs.namenode.secondary.http-address. And I'm going to put this secondary name node on a separate node, which will be this 192.168.0.53:5090. This is the web UI port number for secondary name node. And then this is the checkpointing directory where basically the secondary name node is going to store the checkpoint data, or you can say the backup metadata of the name node. This is the location. So directory where secondary name node stores the temporary images to merge. This is the location where it is going to store the data. This is also what we have created here. Then we'll go into the mapred-site.xml here. So I'll just open the mapred-site and let's see what all configurations we need to do. Okay, so let's first of all go into the job workflow of how MapReduce actually works itself. Okay. So when you run a MapReduce job, what are the different components that it runs, how actually it performs the processing, how it does the processing of the data. So basically, when you have a MapReduce job, okay, it runs various operations in it. Okay, one is, first of all, it runs the map operations. which basically involves the splitting of the large input data set into the smaller data blocks. And it depends upon the input split size you have mentioned. And then it does the spilling of the data. This is basically being done by the MapReduce task IO sort MB and MapReduce task.io sort spilling %. And the idea is that whenever you run a map task, it will take a particular block of the data and starts executing the map task on top of it. So map task is nothing but the user function which is being created by the user for processing that data. And whenever it reaches a certain threshold value in the memory, it will spill that particular data onto the disk. Okay. So this particular part is where all the data goes into the mapper. And whenever a mapper function runs, it uses the memory to process the data. And this task is going to spill the data onto the disk whenever this memory buffer is being filled out. So then the IO sort factor runs, where the idea is that all this data is going to be sorted and created into the partitions. So sorting is done, maybe it can be alphabetical sort, okay? And when the sorting happens, all the similar data is being created into the partitions. And then basically a compare to function is being created to do that sorting thing and to create a partition. So before it writes the data to the disk itself, the background thread will divide the data into the partitions based on the partitioner you have used, corresponding to the reducer where they will be sent. After that, the sorting and partitioning merging phase start, where before the map task itself is finished, the spilled files which are being spilled onto the disk, they are merged into a single partition and sorted output file. Okay, so depending upon like which all similar keys are there, it will generate a single partition file. And the configuration property used for this is MapReduce.task.io sort factor, which controls the maximum number of streams to merge at once. The default value is 10, but then you can always increase it to increase the number of streams itself. And once all these merging happens, the reducer functions will start. Okay, so in the reducer functions, again, it has got a couple of phases, and these all partitions are being sent to the reducer. Okay, so reducer has got basically first of all the copy part, where it will take all these merged partitions and it will copy those partitions here. So each map task output for the corresponding reducer is copied as soon as the map task is completed. And the reduce task has a small number of copier threads so that it can fetch the map outputs in parallel. Okay, and there is another property which can be utilized here, the MapReduce parallel copies kind of configuration, to increase the number of threads that can be used for the copying of the data from mapper to the reducer. And then the reducer function actually runs, where during the reduce phase, the reduce function is invoked itself for each key in the sorted output. And the output of this phase is then directly written into the Hadoop distributed file system. So all in all, in the map function, you will have the couple of functions where you will split the data into the blocks, you will sort the data into the memory, and then you will spill the data on the disk. Okay, this sorting, spilling, merging, partitioning, this is done by the MapReduce framework itself. Okay, by application master in the container. But this mapper function and the reducer function is something which a developer has to write. Okay, and tune also depending upon the kind of the job. Spilling is where all the data, whenever the buffer size reaches a threshold size controlled by these properties, ios.spill.% property, a background thread will start to spill the contents to the disk. So when the spilling is taking place, map will continue to write the data to the buffer unless it is full, and spills are written into the round robin fashion to the directory specified by your local directories you have mentioned in the configurations. And then your partitioning, sorting, and merging happens, where before writing the data to the disk itself, a similar type of partitions are being created for the similar keys, and the background thread will divide this data into the partitions based upon the partitioner you're going to use. Then you have got the sorting. In-memory sort is being created, merging where the spill files are merged into a single partition and a sorted output file. And then the entire data. You can also use the compression here, where the map output can be compressed before it is written to the disk for faster disk writing. You can do that as well. And then the reducer function, where it will copy the data first from the disk to the reducer, and then the sorting happens, and then it is going to run the reduce function on the sorted data. So to complete this entire operation, I mean, obviously we can tune some part of it. First of all, we have to say that the framework it is going to use is basically Yarn. Okay, because Yarn is the generic framework which will execute these MapReduce jobs. And then we are saying that the task IO factor is number of streams spill files to merge at once while sorting the files itself. This is what your task IO factor here is. So generally by default it is 10, but then you can increase or decrease it. And this is the task IO sort MB, which is the size of the buffer itself. Okay, so total amount of buffer memory to use when you're sorting the files in the megabytes. So how it works is whenever the buffer size reaches a threshold size, so like this, your RAM has started filling 20%, and then let's say it has gone to 50%. Let's say the threshold is 80% here, which is being shown as 0.8. So this now has reached a buffer here. So as soon as it reaches a buffer, it will spill the contents to the disk here. This is how the spilling of the content happens. Okay. So after a threshold, the buffer data will spill into the disk by the thread. And this is the spilling percentage here, where a background thread will start to spill the contents to the disk. And when the spill is taking place, map will continue to write the data to the buffer unless it is full. So that part will still keep on going. And this is the local directory where the MapReduce will store the intermediate data files, because the output of the mapper, it goes onto the local disk. And then again, the buffer will start, it will keep on spilling, and the buffer will just go empty. So then you have got the job history address where your job history server is going to run. This is the IPC port, inter-process communication port for the job history server. And then you have got the web application address for the job reduce. So there's a question from our participant. So the question is why we perform the sorting before sending the data to the reducer in the map phase. Yeah, so here you go. So why do we sort this data, guys? Because we want to create a similar type of partitions, and we want to run the shuffle phase, okay, in which we send the similar type of partitions to the reducer. Okay. So with sorting, the benefit here is that sorted output is provided to the combiner function if there is any. And the idea is when these output file partitions are being made, they are being made available to the reducers over HTTP, and the sorted data increases the speed of your entire MapReduce as the data is already sorted, and reducer has to just run the reducer functions on that sorted block of the data itself. Okay, so the benefit here is that obviously the performance of your MapReduce jobs just increases when your sorted data is being presented to the reducer. So for these large jobs, the jobs in which your mapper output is very large, the value should be increased, keeping in mind that it will increase the memory also required by each map task. So the increment in this value should be according to the available memory of the node. Okay. So greater the value of this sorting, obviously the lesser will be the spills to the disk, and obviously it will save the time writing to the disk, and obviously the less the time, more the performance of your MapReduce. Okay. I hope it makes sense. So let's configure this mapred-site as well now. So the same thing I've just configured in the properties here. I'm just going to put them here. So that's your mapred-site.xml. And then we have got the last file, which is called as yarn-site.xml. So yarn-site, this is how the workflow is, guys, of when you are submitting a MapReduce job in yarn. So this is your MapReduce code, and you start your yarn command to execute this MapReduce job. How it works. So you will submit the job to the resource manager. Resource manager will come back saying that, okay, this is the application ID you're going to use. After that, resource manager will create an application master via node manager. So basically resource manager will ask the node manager to create an application master. Now application master is the one who is going to manage the application for the entire life cycle of the application. So application master is being generated in the 4.2, and the application master goes back to the resource manager saying that, okay, I need resources for running the mappers and reducers. So resource manager in the step number 6, it will ask the node manager to create the yarn child containers. So a yarn child container is nothing but a group of resources in the form of memory and CPU. So in the 6.1, application master will start the mappers and reducer task into the yarn child containers. And once all the MapReduce tasks are completed, the output is given to the application master, and application master will put the output into the Hadoop distributed file system. But here, one of the important part is that once the application is being given to the resource manager, the resource manager will connect to the name node to find out the blocks of the data, okay, where the data node blocks of the data are being there. So all these blocks are going to be used to, application master is going to ask the resource manager to create the containers on those nodes where the blocks of the data are. Okay, there is no point in creating the container on node 1 if the data is lying on node 5. So for this, we have got a couple of configurations here. We have got this yarn resource manager address where the resource manager is going to run. I'm going to run it on the node number 52. Then we have got the scheduler address, which is used for the scheduler interface in resource manager. Then you have got the resource tracker address, which is being used by the node managers to connect to the resource manager. Then we have got a couple of configurations related to our logs. Okay, if you want to enable the log aggregation, you will just generate this file, remote application log directory. This is where all the logs are going to be aggregated in the HDFS. This is the directory name, and this is the node manager logs where all the container logs are going to be stored. Then you have got the log server URL, which is being utilized by the job history server. Once an application is completed, all these jobs or the applications goes to the job history server, and job history server will keep the history of the jobs by using this URL. And then we have couple of configurations for decommissioning purposes. And this is the configuration. The last configuration is for the minimum allocation for every container request in the resource manager. So basically, minimum memory you want to be given to the container. As I said, container is nothing but a group of memory and CPU only. This is the minimum memory in bytes, and this is the maximum allocation memory for your container. This is the entire node manager memory. So generally the node manager memory is much more than the maximum memory you allocate for the containers. And this is the maximum allocation, because you can also define the minimum vCores also for a container. Here we are defining the maximum allocation for every container for your yarn child container you're going to start in the cluster. And let's now complete this configuration as well. So I'm going to utilize this yarn-site.xml. Okay, so all these configurations are being completed now. So the next part is basically to create 6 hosts, and these kind of hosts now we have to create. So what I will do is I will just stop this node, and what we are going to do is we are going to create 6 copies of this node itself, because all the configurations is there. So we'll just say nodes. So I'm going to create these nodes here, and we are going to create 6 nodes, guys. So we'll have name node, we'll have resource manager, we'll have secondary name node, data node 1, data node 2, data node 3, and one edge node, data node 3. There you go. Okay, so what we'll do is we'll just try to create a clone of this virtual machine. Cloning is done by using the VMware workstation itself, where you can say VM, manage, and then clone. We'll just use this to create first clone of our virtual machine. And what it will do is it will create these virtual machine files here. Okay, so we'll do this 7 times in total, because there are 7 nodes. So this is for the resource manager. We'll use the resource manager folder, and this is also been created. So now we'll use it for the secondary name node, and this is the secondary name node. So what it is doing actually, guys, it is just creating a similar virtual machine, a copy of this virtual machine. And for every virtual machine, because the IP address is copied as well, we have to just change the IP address and the host name of the virtual machine as well. And here you can see second virtual machine is created, and now the data node 3, and we'll also create one gateway node for our developers. There you go. So now we will just start these all machines, and the next step would be to change the IP address and the host name of every host. Now this is the more of a Linux administration activity, guys, and a networking activity. And generally the files which we edit in this is etc sysconfig network scripts, if CFG, whatever the Ethernet card you're using, ETA0. So I'll just quickly show you one file here, one node. So this is the file we're editing, if CFG-ETH0, and here the IP address, I'm going to change it to 51, because this is what for the name node I'm using. And the host name here I'm using is nn.cluster.com. That's our host name. So save and exit and restart your node, and it will automatically assign this IP address and the host name to it. And what we have to do is we have to create the same thing for all the nodes. So 52 is for the resource manager. Let's say this is the resource manager node. This is the secondary name node. This is the secondary name node here. This is the data node. So same thing, I'm just doing it like 7 times, because all these configurations have also been copied automatically. We have to just make sure that our configuration is aligned to our planning as well. So we have planned these all nodes. 57 is for our edge node. So all the nodes are almost completed now. And what we can do is now we can run a small for loop to find out whether our nodes are created successfully or not. So I can simply say here node number 51, and we will say here for I in 1 to 7 do SSH of 192.168.0.5 hostname -f on every node. Okay, so you can see it is creating a host name. So you can see all these 7 hosts have been created with their respective host names. We can also run the host name -i to see the IP address also. And you can see the IP addresses have also been created accordingly. Okay. Once this is done, we can now switch over to our Hadoop user. And the next step is to run the format command. So we'll say here HDFS name node -format. This is basically to initialize our file system. So we created 6 copies of the virtual machine. Now we're going to format the name node here. This command will format my name node, HDFS name node -format. And here, if you get this kind of message that storage directory has been successfully formatted, that means your file system has been initialized successfully. And now we'll run the scripts called start-dfs.sh to start the DFS. And here you can see it is asking us to start the name node, 3 data nodes, as well as, okay, we forgot this. You can see here why it is connecting to this local host here, because we forgot the slaves file. Okay, that one file we forgot. And that is the reason it's trying to connect to this local host. So what we need to do is we need to edit our slaves file again for the resource manager as well as the name node so that the appropriate data nodes can be started. So we'll say here slaves 192.168.0.54 because we'll have 3 data nodes 54, 55, 56. And we'll also go to the resource manager to copy the same thing 192.168.0.54. 55 and 56. So 3 node managers will be there. I'll just run the start DFS again so that it can start 3 data nodes on the respective machines 54, 55 and 56. The other daemons will remain as is because they're already there, so they are not going to restart. Obviously you can see it says secondary name node is already running as process 140. It stop it first, so that's fine. So now if I want to monitor whether all these processes have started successfully, I can say for I in, or I can simply copy these hosts here and I can create a nodes file. And here I can say for I in cat all these nodes, do $i and give me the host name of this host, run the JDK command to find out the process running on this host and create a new line just to give a good output. So you can see here that we got 3 data nodes, and you can see 1 data node is already running because earlier we didn't have that proper slaves file. So we can just kill this one because our planning is that we'll have 3 separate nodes for our data node. So now we'll just run this again. And there you go. You can see 1 name node has started, 1 secondary name node has started, and 3 data nodes have started according to the plan we had. And there will be 1 name node, 1 resource manager, 1 secondary name node, and 3 data nodes. Now we'll go to the resource manager part, and now we'll start the yarn processes. So here I'm trying to start the yarn processes, and now it is executing. So here we'll just run this command again, and now you can see here the resource manager has started on the resource manager node, which is rm.cluster.com. Then you can see 3 node managers on data node 1, data node 2, and data node 3. So 3 node managers have started. And also on resource manager, we'll start the job history server by running the start history server command. And again, we'll run the JPS command to see. So you can see here the job history server has also started on this node. Okay. So that's how you will build the Hadoop cluster, guys. That's how you will have the Hadoop cluster. I'll go through this commissioning, decommissioning part in a while. And before that, I just want to show you the web user interfaces as well, which it generates. So we have the web user interface components also, which are being created here. So name node web user interface goes to the 50070 port number, and resource manager web user interface goes to the 8088 port number. Secondary name node web UI goes to the 50090 port number, and job history server web UI goes to the 19888 port number. So we can see all of them now because we have started our daemons. So 192.168.0.51, 50070 is for the name node here. You can see this is the name node web UI, which contains your overview of the name node as well as the summary about the storage we have. And then we have got the group of data nodes which are being connected to it. You can see it is showing 4 data nodes because this data node was created by mistake earlier. And we'll go to the resource manager, which is on 8088 port number. And here is a resource manager with 3 nodes on it, 3 node managers. You can see 3 node managers as well. And then we have got secondary name node, which is on 50090. So here you can see the secondary name node user interface, which is connected to the primary name node here. And then we have got the job history server, which is on 19888 port number. There you go. You can see a job history server for the MapReduce job, for storing the history of the MapReduce jobs. Okay. So these nodes have been created now successfully, guys. That's how you will build the Hadoop cluster. Now the idea is how will you add a new node itself to the Hadoop cluster if you want? How will you commission a new node? How to increase the storage of the cluster itself? So the next part, guys, we are going to talk about is the storage part. And before we go into that, the important thing to understand now is to see what is the total storage itself on our node. Okay. With the total storage, we will be able to understand that if I want, let's say, to increase the storage of my HDFS, in a sense, I need more storage to my cluster. There are two ways: either increase the storage of the existing nodes or add a new node itself, whatever way you want. Generally, we add a new node because it gives us the more storage as well as more capacity in terms of processing. You can have more RAM to it. You can also have more hard disk to it. So you can have more CPU as well. Okay, so that way you can increase the storage of a cluster. So first of all, how to find out the current storage part? If I want to find out the current storage, guys, we can go to the DataNode web user interface, and this is the configured capacity. This is the total capacity we are having right now for our cluster. Okay, and this is the amount of non-DFS being used, and this is the amount of DFS which is being remaining right now on our cluster. Okay, so the next thing that we want to do is we want to add a new data node to our cluster, and we also want to add a new node manager to provide more memory and more virtual cores. So how we can do that? So the commissioning of data node is something like this. So this is your name node here. We want to add a new data node. This is how the commissioning runs. You will add a new data node. You will run a utility called balancer so that the old data can be moved to this new data node. This is how the process will be. You will update the hdfs-site.xml. You will update the yarn-site.xml with these configuration properties. And then you will add the data node IP addresses to the includes file. And then you will update the DFS admin reports. You will run this command DFS admin refresh nodes and the yarn RM admin refresh nodes to add this new data node and node manager. So let's go through this one by one and see how it actually works. So give me just 1 second, guys. First of all, guys, what we have to do is we have to create a new machine itself. Okay, so what we'll do is we'll go into this our folders and we'll say here new node, and what we'll do, we'll create a new copy of this virtual machine. Okay, obviously in the real time you are not having the privileges of creating these virtual machines and cloning them. So what you can do is you can just add a new machine, and then you can create the same user and same group, copy the same binaries as well. So you can do something like that. So in this scenario, because we have a virtual machine, we are able to create the clone of it. And what we are going to do now is we are going to update our etc host file first. Okay, so let's say the IP address of this new node is 58 and the new node is this new node. Okay, and I'll also copy this. So first of all, we'll change the IP address and the port name of our new node. So we'll say here IP address is 58 and the host name is new node itself. There you go. Okay, so once this is done, we will be able to copy this now file on all the nodes. So for I in, so I'll just copy this as well, etc host, and we will just copy this. We'll just copy this host file to all the nodes. And the last node is also done. You can see here, the last node is also done. So now I can SSH into my new node from here itself without anything. There you go. So once it is done, the next part is to update the hdfs-site.xml. And here we'll add a property called dfs.hosts. And here we'll try to include a file. So we'll say here /home /hadoop /hadoop /etc /hadoop /includes. Now this is the file, guys, we have to create, in which we will add basically all the hosts, including all the data nodes. So we'll say here 192.168.0.54, 55, 56, and 58. These 4 hosts we are going to add. 3 are already there, and 1 we are going to add here. And in the resource manager, we will do the same thing, etc hadoop yarn-site.xml. And here we're going to add a property. I'll just copy from the node, and the file here is, we can put the same file here as well, home hadoop etc hadoop includes file. So we'll just open this file here. and we'll add a new node 54, 55, 56, and 58. So once this is done, the next thing is to refresh our nodes. So we'll basically use this thing. We'll say here, so previous configurations, you can see here we have got 3 data nodes and we got 3 node managers running. So on name node, we'll run hdfs dfs admin -refresh nodes. This will add a new node to my cluster because it will include the includes file. And once it is done, you should see the 4th host. There you go. And you can see it in a dead mode right now because we have not yet started it. So we need to start it as well. And on the resource manager also, we'll say yarn rm admin -refresh nodes. So this will refresh my resource manager as well. And you should be able to see the 4th node. It's not there right now. It will be there soon. So once it is there, in fact, let's do one thing. Let's just start these new node. So we'll say here start data node. We have to start this manually, and then we have to start our node manager as well. So we'll say yarn daemon.sh start node manager. Okay. And now we can just run our for loop. We can say 58. And here you can see now the 4th node also has got this new node. And you can see here this new node has been commissioned now in the resource manager. And it is there now in the list of these data nodes, which is there in the name node. So basically you are able to add the extra storage. And obviously now the storage has been increased from 75 gigs to 100 gigs. Because this new node storage has also been added here. Okay, so the idea is again because we were already having a lot of configurations there in our new node because of the cloning operation. So we did not really bother about creating the user or adding the same binaries, adding the same configurations. But in real time, obviously, you have to copy all these configurations. Once you're adding a new node into the cluster, you have to add all these configurations from the existing data nodes to the new node. Another thing is, once you have added this data, obviously the existing data will not start automatically going to this new node, new data node. Okay, so you have to run a utility called balancer so that existing blocks can also be moved to this new data node to maintain the replication and to maintain the balance between these data nodes. Okay, for the data. So this is how you will commission a data node, guys. Let's go into the part of decommissioning a data node and node manager. Basically means you are removing an existing data node from the cluster because let's say you want to do some maintenance activity. Okay, the reasons can be really anything. In this scenario, let's say you want to do the maintenance activity on any data node and you want to decommission the data node from the cluster. This is a graceful decommission, guys. We are not switching off the data node. We are taking it out from the cluster by running the Hadoop commands itself. Okay, so in this case, the data will automatically be replicated to the other data nodes and there is no balancer required to run in this kind of activity. So how to decommission a data node? Let's say I want to decommission the data node 1 from the cluster. What I would do is I will update the hdfs-site.xml and here I would say dfs.hosts.exclude. Okay, and here instead of the includes file, I will create an excludes file. Okay, and in the excludes file, I will provide the IP address of my data node, but make sure that it is not in the includes file. Otherwise, name node will be confused, right? So question from our participant, does the node manager daemons also get decommissioned when we decommission data node? We have to create it separately. So we have to go to the resource manager in the yarn-site.xml and they will be decommissioned automatically. Yes. So I will just say here this property. And here is my excludes file. And here we'll provide the 54 as our 54 as the IP address of the node manager, which we are decommissioning, and we'll remove it from the includes file. Basically, we'll follow this part here, dfs.host.exclude, and we have defined the exclude path for our excludes file at the data node IP. We have done this part as well. Now we are going to refresh the nodes again. So right now, guys, you can see that data node 1 has got this data node and the node manager running. Now this is what we want to decommission from our cluster. So what we'll say here, refresh nodes, which will decommission our data node. And you can see now the data node has gone from our data node 1 automatically. And we'll also do for the resource manager, refresh nodes, and it should decommission my node manager also. And here you can see the node manager has also been decommissioned from the cluster automatically because we just refreshed our files. You can see the same thing obviously from the web UI as well. So the DataNode 1 has gone from here, and in this scenario also the DataNode 1 has been decommissioned from our cluster. So all in all, basically you are able to decrease the storage of your cluster because of you have decommissioned the data node, and it will also decrease the capacity in terms of processing because the node manager has also been decommissioned from the cluster. Okay, let's do a recap first about the Hadoop architecture. This is what we have created. We were able to create our name node, secondary name node, job history server, resource manager, and couple of nodes we have with the node managers and the data node. We can run a small job also to see yarn child containers. So we can simply run a command yarn jar Hadoop share Hadoop MapReduce. And what this will do is this will generate the yarn child containers also, which I will show you from here. So I'll run a job here, and this is a pi job, which is actually going to find out the value of the pi. And once this application will start, this application is going to start the application master, as well as you can see here, an application master has been started successfully. And it will start the yarn child containers also in a while. There you go. So you can see now yarn child containers have been started as well to find out the value of the pi with the 10 samples. So this is how it works. And this is what we have discussed in our past an hour or two, that how these daemons have been created and how these application masters and containers have been created. So this is the entire architecture of Hadoop cluster, guys, Hadoop version 2, which is the latest one. So the common Hadoop job responsibilities, in the conclusion, I want to say that Hadoop administrator is responsible for implementation and support of the enterprise Hadoop environment, which consists of your web user interfaces, which consist of all the Hadoop ecosystem components, security, performance tuning. A Hadoop administrator has to implement all the concepts of Hadoop and its ecosystem components. He's involved in the capacity management, designing, all kinds of monitoring and structure planning and scaling of the Hadoop cluster. He's responsible for user management. He's responsible for all the application support of applications which are being integrated with your Hadoop environment. And Hadoop administrator is also responsible for all the kind of management, monitoring, and analyzing the file system and log files. On a day-to-day task, he has to manage the user jobs running in the environment, make sure the environment is healthy and it is able to run all the jobs, add the users on a daily basis required, create the kind of scripts to add the users or monitoring the clusters, and provide the recommendation to the developers about the environment, how they can utilize it in a best and efficient way. So this is what we have, guys, for our class. Thanks a lot for joining in, and if you have any questions, any queries, or any feedback, please feel free to use our tools to provide those feedbacks there. Thank you very much. Have a good day and good night. Thank you very much. Bye-bye.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!